So, for example, if the application goes down at some point, you don't want to start reading messages from the beginning of the topics or the queues. So this kind of scenarios, how we handle that. Those are the things that we need to look at. That has some programming that you need to take care of and things like that. So what I'll eventually suggest is, I have this code on GitHub. If somebody wants to just go run it, you can take this code. We can, as a group, assemble back again, improve the code and things like that. The code is there. Pick it up, make improvements, share it with everyone. That's the idea. So Spark Core, we'll just do a quick overview of that. We will look at the basics of Spark streaming. We'll look at Apache Kafka, which is a streaming paradigm. And we use Spark Kafka and we use Spark streaming and Kafka together in this application. We will run this on Google Compute Engine, which is the cloud offering of Google. And so what I'm going to run is not a cluster, it's just one machine on Google Cloud. And transforming this to a clusterable application is very simple. We'll just point that out, and then maybe in the next few iterations, when we gather, we can have a whole clusterable application with all the bells and whistles. So we'll look at the code itself, and we'll talk briefly what we can do next. If you're interested to get your hands dirty on the code and things like that. Okay, so Spark streaming world looks like this. You have Spark itself is a programming paradigm. Like it gives you a framework for developing and running distributed applications in memory on a cluster. Now, Spark streaming is built on top of that. So what Spark streaming allows you is, it can take real-time data flowing through various channels. One of the channels is Kafka, and that's what we are going to discuss today. So your channels can be, if some of these names don't make sense, just don't worry about it. So your channel can be an ACA program, which actually is an architecture based on you design your whole application as a set of actors contributing messages to other actors and things like that. That's how you design it. And with that kind of setup, you can have a streaming application coming out of that. It can produce real-time data. And this icon is Amazon Kinesis. It's another streaming application that's an offering by Amazon. Kafka is an Apache project, and Flume is another streaming project. So you can have data sources like this, which are real time, or you could have data sources which are just databases like HBase or the more traditional MySQL, Cassandra, or MongoDB, or whatever, or just plain files. So you could stream your data from these sources, and then while it streams, you do the processing. And while processing, you can also apply your machine learning libraries, machine learning algorithms that are a part of your Spark ML lib. And you can actually have your Spark SQL. I mean, if you read data, convert that into a data frame, you can actually run queries within your program on that data frame, or join it with some other data that's coming from another database. Do things like that. And your syncs can be any of these. Again, you can send this out into a stream for another downstream process, or into data syncs like this, file streams or RDBMS, or databases like Cassandra, or there are so many databases. You could use any of those. So this is how a Spark streaming application will look like. Well, I just mentioned the Spark streaming data uses the familiar Spark core API, machine learning libraries from Spark, etc., and also GraphX. Preeta is going to do a presentation on GraphX next week, next Sunday at 12 here. And what you can have streaming data that can go into your training models. So that's something you can do. And your trained data can feed into the Spark streaming process. So it's kind of training on the fly. That's something you can do. You can actually query interactively, the data that's flowing through. For example, you can have data flowing through the queues. Your Spark streaming can maintain some statistics while the data streams through, and then you can run a query on that, for example. And use cases, intrusion detection. Like let's say you have some adversary logging into your system, and you detect something unusual, the location from where this happens. Like things like some hacker gets into your system, and there's something that you have here that can identify that this is an unusual activity and flag that. So that's something you can do. Log processing, web logs, they're huge. I mean, they keep getting created. The most popular websites will have so much going on, and that's a lot of processing. Fraud detection while it happens. So that's the idea. And IoT, Internet of Things. If you have a manufacturing line, assembly line, you can have sensors there that keep sending out data, and while the line is operational, you can detect unusual things, so which if you can match that to some patterns, you will be able to detect some anomaly in your manufacturing and things like that. So the applications are huge. Recommendations derived from data collected from wearable devices like your Fitbit and those things. Yeah. Websites, analysis of click streams. So these are just the applications. Sentimental analysis. Which companies do, like whether people are feeling good about some product or not, and things like that. And mobile devices, when you walk into some food court, you may get a recommendation on some promotion that's happening within that, in some restaurant or things like that. So there are many. Okay, so let's look at Spark Core. The basic abstraction in the programming model for Spark is RDD. RDD stands for Resilient Distributed Data Set. So what an RDD is, it's a data structure that can be written down as think of that as an array of objects. And the array of objects will be distributed on a cluster. So pieces of it sit on different nodes. And from your program, you can operate on that RDD as one entity, like how you can operate on a list within your one node program. So things like, you can say, take this RDD, take each of the objects, map them into a different object. That's something you can do. So you get a mapped RDD. Or you can say, take this RDD, if you have pairs, key value pairs within that, group by key, and give me the sum of all the values for a given key. That's something you can do. And so Spark is very good at that kind of programming paradigm. It does that in memory. So, and that's super fast. And the kind of operations you can do are transformations, which are mappings. So you take an RDD, map that into another RDD. Actions, well, these may not make sense, but you need to see some examples to see what these are. Like actions could be summing up according to a key, or taking the RDD, writing it to a database, or writing that to a file system. Those are the actions. And while you do computations, since this is distributed, you cannot have one variable available to all the nodes. So you have the concept of a broadcast. So if you want some data to be available across all the nodes, you just take that variable and you have something called broadcasted. The same data gets to all the other nodes, and they are available to your RDD operations within those nodes. And accumulators are things like, for example, in a program, you can have a counter. So as you process this, if you have a multi-threaded program or something, you can actually lock a variable and increment that variable by one. When some processing happens, release the lock, have another thread do the same thing, and things like that. So you can synchronize access to a variable, and then it probably gives you the status of your application's progress or something like that, right? So you cannot do that with a straight variable within your program, because these things happen on different nodes. Spark gives you a structure called accumulators, which should be a variable which sits inside of the driver program, which actually drives the whole node operations. And from there, within the operations on the node, this variable can be updated. So this is some structure that you need to be familiar with Spark programming. And shuffle is when you have an operation like take this RDD, group it by key, and then do some kind of sum. If you have that kind of operation, for the same key, you may have key value pairs sitting on different nodes. So this RDD has to shuffle data between the nodes. So shuffling is something that happens based on actions like reduce by key. And partitions are, like if you have an RDD, you can partition it the way you want, so that each partition gets work parallelly, so that you get very high concurrency. So you may have something like this. An RDD is sitting on 4 nodes in a cluster, and the number of partitions may be 20. So that means each node has 5 partitions of that RDD. And when you run your map process, so all those 5 partitions will go into that process simultaneously. You have 5 of those things happening on each node. So you can have very high concurrency. And RDD persistence is the same thing. You can persist data into a file and things like that.
Sorry, Joseph. We got a couple of minutes. Some more jokes coming up on the way for right now too. Right here, I have a double double. Sorry about the weight class we have. We have a cappuccino here. Coffee with cream. And as well as I have a hot chocolate made with almond milk. So with cream. Okay, we got a couple more just coming out there now. Okay, thanks for your patience, guys. You guys, you want to write up here though? You guys, you want to write though?
Yeah. So it is the process here. It's very similar to the Hadoop.
Yes, yeah. I mean, well, Hadoop just gives you a platform, right?
Yeah.
So you could run on a Hadoop cluster. You get two things. One is your HDFS, your file system, which is distributed. You also get what's known as yarn. Yarn is basically your resourcing engine. So if you submit a job, you need some resources for the job to run. So that you can think of that as an operating system, a cluster operating system. So on Hadoop, you can run a MapReduce program, right? So here, your transformations are like maps. You take an RDD, map that into another RDD. And your actions can be one of your reduced processes.
So you do any mapping here?
Yeah. I mean, your transformations are mapping.
Okay.
You take an RDD, map that into another RDD, where each element is mapped into something. So it's a one-to-one operation. So if you have an RDD of size 1 million elements, when you do a transformation, you get another RDD of 1 million. Or more, where there is something called a flat map. You can take an element, stretch that out into more elements. If you do that, you get another. So similar to any mapping process in your MapReduce.
So here, like, let's see, I'm familiar with Hadoop, but when people say like these days it's Spark.
Spark, you compare Spark with MapReduce.
Sorry?
You compare Spark with MapReduce.
Yes.
Hadoop is a framework. So when you say maybe you're familiar with MapReduce.
Yes.
Yeah, well, MapReduce corresponds to Spark.
Yeah, MapReduce is obsolete.
MapReduce reads from a file. With each MapReduce, it goes back to your file. So your I/O is very costly, like because reading from a file is not. I mean, it's not very quick. But what this does is it takes data from a source like a file system, like MapReduce. If you have an operation like reading within Spark, just read that and then persist it. Probably this will be perform the same way as MapReduce. But then once it reads into that, it's available in the memory, and your operations all happen in memory.
So does this depend on using a specific programming language?
Programming language, in this case, you have a choice of Python or Scala or Java. Yeah.
As soon as you start,
Please come.
nothing is happening behind us.
Is that a nice latte here, guys?
Ice latte? Yeah.
It's really beautiful right there. I got a coffee here as well. I got a chai latte as well. Thanks so much. Thanks for your
Doing some operations.
Thanks, guys.
Nothing is happening. Just drawing it now. It's just drawing the steps. Then it is saying even at that time, nothing is happening. It's just drawing this stack. Then at the end, maybe you are saying come. That's when it begins the process. So till then, nothing is happening. It's fine. It's fine. So it's fine. Each step is treated as a graph. Only when you fire the actions, that's when it is actually doing something. Whereas in MapReduce, it's like it's there and there. And it's in your
It's called a lazy evaluation. So what it does is it groups all of your transformation. Just a record of what you want to do. It just keeps that.
So a transformation is not code, it's just graph.
Well, your code gets.
You're writing code, but the code is setting up a graph that Spark can compute on and do more advanced things.
Only when you write your actions, maybe to collect latency or data or how. That's when it is high.
Yeah. So well, you can think of most of your computing as graphs, like directed acyclic graphs, right? So start with this, combine these results here. You know, that's a graph, right? Yeah.
So, but here, as a Spark, you run it in a single machine.
Spark is distributed. You run it on a cluster. Same as that. Yeah. You can run it on a Hadoop cluster. Spark can also be run on a cluster of its own. If you have all nodes with just Spark on it, you can run it on that. Or it has many options. It has another option. There's another operating system called Meetup, which is not Hadoop at all. So that also gives you a cluster with an operating system on top of it. You can run Spark on that.
Maybe it's wise to shift
Yeah, so it's just faster because here it's not lazy, it's just the map reduce. You have to do the step by step.
With MapReduce, if you have 10 steps, in every step data has to come from a disk, then go back to disk.
Yeah.
That's very slow.
Yeah, on the Spark you don't have to do it.
It just reads it in memory and everything happens in memory and then goes.
Go back to the house.
Basically, the data inside is Spark.
HDFS. You can have your Spark cluster, Spark running on top of Hadoop cluster. Like you can have your Hadoop, Spark programs provisioned by Yarn in Hadoop. You don't have to do that. So today I'm not going to use Hadoop at all, like for running it. So Spark streaming is this. You can have sources like Kafka, Flume, and these things, Twitter, for example, and they flow through your process. And this is like a process that keeps running all the time. It's a 24/7 process. So something comes in, it processes and sends out. So that's the paradigm here. So your sinks can be HDFS, databases, or it could be dashboards. So internally, Spark streaming works this way. Your input data gets into Spark streaming. It's broken down into batches. Each batch is an RDD by itself. So think of each batch as each batch is time sliced. So if your batch frequency is say 30 seconds, so it collects all the data coming in for 30 seconds, makes an RDD out of that. And your RDD again, as I said, RDD is cluster. So your data can be coming into the cluster. They'll be filling up the nodes. Well, some data structures in different nodes. And after that 30-second time slice is over, there's a cutoff, and you get an RDD, and you basically process that RDD, and then go for the next 30 seconds worth of data. So that's how it works. If you want really high, if you want really low latency, you make that 30 seconds as 100 milliseconds. So every second it will make 10 of those batches. 1 second.
So when you said Spark streaming, it has to be coming all the time, like 24 hours. So you don't use it for data, it's just for
you can use that also. Like in the earlier diagram, you actually saw your data can be files coming from files on HDFS, or it could be any NFS system, any of those.
It could be waste of time to use it in this way, or it doesn't matter.
It doesn't matter. sometimes you may want to have data coming from a file system. You may want to pick it up as soon as some file comes in. So when that's your need, you could do that, and you can combine multiple streams of data. One coming from a Kafka topic, one coming from a file system. Take all this in your program. Do whatever you want with them, and then process it. That's something you can do. Okay, so that's about Spark streaming, at a high level. Kafka is a distributed streaming platform. So what it gives you is a mechanism to publish and subscribe to a stream of records, and a stream of records that you can identify by a name. That stream of records is called a topic. So, and it has some fault tolerance and things like that. This slide? Yeah.
So when it is divided into time slots like here, 20 seconds.
Yeah.
What is the next piece? What is the next? Can you complete that diagram?
Okay. So this Spark streaming process creates the batches, right? So it's time sliced batches. And this Spark engine, this is something that you implement. So you will implement logic on what you need to do with each batch. So you're processing logic goes here. With each batch, what do you want to do? You want to take that, do some processing, add the stuff coming here to an existing status. Things like that. For example, if it is Twitter streams, and if you have like one of the messages, a good one is a bad one according to you, identify that using some learning and then update the number of good messages, bad messages. You may have a counter like that. And then you can also have a query engine that says, give me the status now, which comes back and says you have this many good messages so far, bad ones.
Or it could be a log.
Oh yeah. So yeah, it could be that. Yeah. So Kafka is a different application altogether. It's another Kafka. It's another Apache project. It allows you to publish messages on a cluster for a given topic. You identify a stream of messages with a name and you call that a topic. You can publish messages, and the messages, Kafka makes this fault tolerant, which means it maintains a replica of the message on different nodes. So if one node goes down, it still knows how to get the same message on a different node that's up and running. So it's fault tolerant that way. And it allows for processing streams of records as they occur. And runs on a cluster usually with multiple servers. And it also keeps a log of what messages came in. So when a message comes in, it passes the message into a log. And the log is on HDFS. And you can set how long the log should reside. You can say purge the messages more than 7 days old. You could have something like that. So for 7 days, any message that came in will stay on the cluster.
By default.
By default.
Spark assets, they say it's called.
Well, this is nothing to do with Spark. You can have a Kafka program and a Java client, like Java consumer and a Java publisher. You don't have to do Spark at all.
So Spark doesn't come with Kafka.
Kafka is different. So Kafka is different. For the Spark streaming, I am using Kafka as the source of data, streaming data, in this demo. And each record consists of these things. It will have a key, it will have a value, and a timestamp. Timestamp says at what time the message came in. So Kafka has 4 APIs. If you have a Kafka cluster, and if you created a topic, you can have producers. So you can use the API to produce messages to the topic. And connectors are basically, you can have stream your data into Kafka from a database. So Kafka has connectors. We're not going to go into that today. And stream processors, again, if you want to publish this to another stream or read from a different stream, you could do that. And consumers are, just the consumers of the messages. And so what we are going to see is producers and consumers today. Yeah.
Kafka is like, if you're using Spark, would you use Spark API to read messages?
I'll use a Spark Kafka connector to get to Kafka messages. Yeah. Twitter?
Suppose you're getting the stream from, you're using Kafka.
No, Twitter is different, right? I mean, I can have Twitter messages flow through a Kafka queue. That's a different thing altogether. Twitter is just one app sitting there. I don't know if Twitter gives you messages on a Kafka topic. I'm not sure of that. So this is just any Kafka, any message that you can use using Kafka will give you a way to publish messages to a topic, and then it will also give you an API to read messages. And Kafka can be deployed on a cluster on Hadoop.
So can we say like when we install Kafka, but you install it in each node, or you have to be in the
On a cluster, you need to have Kafka brokers on each node. Yeah.
So I'm just thinking about this Kafka is like the master system.
Kafka, yeah, I mean, this again like distributed structure.
Yeah.
You can have brokers sitting on each node. So usually the Hadoop processes like this have something called a zookeeper, which will keep a tab on which nodes are running, which are not. So it will keep pinging them, and it listens for heartbeats from all those. If a broker goes down, it switches to others.
Yeah.
So behind the scenes, it's complicated.
Yeah.
Like it does all of those things.
So it's Kafka similar to this procedure.
Kafka usually works with a zookeeper.
Oh.
So messages, a topic will be partitioned. You can create any number of partitions, or you can just work with one partition. If you have one partition, that means you're using only one node in the cluster. So if you have 10 nodes in your cluster, if you want to distribute it evenly, you have to make sure you have at least 10 partitions for your topic. So Kafka writes messages on HDFS like this, and these are called offsets. Offsets are just the position of a message in each partition. And so when a consumer reads from a topic, you usually, if you have as many consumers as partitions, Kafka will make sure that it ties up one partition with one consumer, so that you can have parallelism affected. If not, you can have all the message. If you have just one consumer and a Kafka topic with 3 partitions, all of these 3 will have to go to the same consumer. And Kafka will maintain another log with internally to see which consumers consume which offsets, and it will make sure it doesn't hand over the message that it has already handed over earlier. So it does that. But for that, consumers have to do something. They have to go back and say, I consumed up to this point. That's something a consumer has to do. And consumers are grouped by, consumer group IDs. So you could have one topic where messages are flowing in, and you may have like more than one application wanting to read messages from that. So you want to separate them out as different groups, right? And within each group, you can have multiple consumers. For example, Group A can be one application that has 5 consumers. Group B can be another application that has a different number of consumers. So within Group A, Kafka will make sure that it hands over a message to just one consumer. So it doesn't duplicate the messages between consumers. And so Kafka has that built-in feature. So in this case, you have a Group A having 2 consumers, C1 and C2. And if you have message here from a partition P0, it ties up with C1 and C3 here. This is how it works. It makes sure that messages from partition 0 don't go to a consumer that's not handling it. So this is again, this is the same picture. I just put it there just to give you what's going on. So Spark streaming. So our use case is Spark streaming using Kafka, and Kafka uses consumer API, which is a part of your Kafka API. And I have this code on GitHub. If you want to just, I'll post this PDF also on website. I'll let you know, so you don't have to note it down now. So this is some project you can take, run your code, and then during the next sessions, if somebody has interest, we can improve on this. Okay, so let's actually do the demo. Okay, I have like 20 minutes. I hope that's enough time. So that's my Google Cloud account. So you could do the same thing on I could bring up a Dataproc cluster. Dataproc is Google's offering of your Hadoop clusters. So I could bring up a Dataproc cluster, but today, I'll just bring up one machine that has all of these things. So and sorry. Actually, charge is not much. I mean, if you see, like I probably used it for a day or so from the beginning of this year. They've charged me 50 cents so far. So, yeah, I mean, not a whole day. I probably used it for a couple of hours or 1 hour or something like that. It's pretty cheap. So let me start the machine.
So you download the Spark in the virtual machines?
Well, I actually compiled my program using Spark libraries.
Okay.
And all that I need is Java 8 on that machine. And when I compile it in such a way that it brings in all the libraries into the jar file. So I create what's known as an Uber jar. It brings in all the dependencies that it needs. I just take the jar there and run it. That's all I do. I hope we'll have some time for the code itself. We'll see. Okay. So I basically need 3 terminals. I need to change something because whenever I start the machine on Google Cloud, I get assigned a new external IP address. So the internal IP addresses will remain the same. So I need to change some setting here.
So you don't have to really download the virtual machine in your computer. Use first.
Well, this is already a Linux machine. Well, this of course is a virtual machine on Google Cloud, on the cloud. Yeah.
Okay.
Yeah. You don't have to download any VMware and all that stuff.
That's like because you use Google things.
Yeah.
Oh yeah, I have it. I have the Hadoop in mind.
So I am actually setting this up. I'm editing the config for a Kafka broker so that it's accessible from my machine here. So let me. So as I said, this runs along with the Zookeeper. So if you look at this command, what I'm running here is a Zookeeper application. I can publish these comments as well. Like it takes a while to write these comments, so I just put them in a text file and run it. But I can give you the details of how to run this. So I just started the Zookeeper just now, and I'll start the Kafka broker. Okay, looks like it's running. So I have, this is another tool that you can install, something called Kafka tool. It's called Kafka tool. Sorry. So, okay, I need the, so Kafka tool gives me the ability to connect to the brokers. Oh, sorry. So this tool is running on the machine, on this laptop. So it is going across the internet to connect to connect to the Kafka broker that's running on the cloud. So I'll create a topic called test topic. This is a Kafka topic. I'll make it into 2 partitions. So this is a topic with 2 partitions. So if you look at it, I have this test topic with zero messages in there. So there are no messages right now because I haven't produced any messages on the topic. Now to produce messages, you know, that's what that code on GitHub does. You know, I'm going to share that code with you. So I'm going to run a producer on one window and a consumer on the other window. So my code is structured this way. So I have the source data here. My target has the compiled program. Sorry. So this is the Uber jar file that I mentioned. So this jar file has all the dependencies. So when you build your program, you build it in such a way that it brings in the dependencies in your jar file. So let me start the consumer first. So that starts the streaming application, and you know there are no messages yet because I haven't published any messages. Okay. Now I'll run the producer. So a producer ran, you know, it quickly produced 1,000 messages. So to see what messages were produced, you know, it has 1,000 messages there. So my messages, okay, I think I need to do something more here. Let me put that in the string. Okay, so my messages look like this. Offsets for each partition, you'll have an offset. So you have partition. So this at the beginning, it's showing partition 0. So you have an offset, which is the position of the message in the partition. And in my program, I generate key value pairs and publish it to the queue. That's all I do. And my key value pairs look like this, you know, some message and things like that. Now, what did the program do? You know, in my program, if you look at the code, you know, it takes messages from a Kafka partition and persists that into a database. The database I'm using here is Postgres. So let me connect to the Postgres database and see what it did with the messages. 10 more minutes.
That's running.
Sorry? Database is also on the cloud. Fast TV. Something is not right. Oh, I think I did something that I need to. Okay. Setting up Kafka.
We have another 8 minutes.
Yeah, I think I need to rush. Okay, I think I need to. I'm not sure why I'm not able to connect to the Postgres server. But anyway, the idea is the streaming process, persisted the messages. I'm not able to get to the database though. Anyway, I'll leave it at that. So we can. Well, I'll try to complete this demo some other time. So it takes the streaming application. So if you would want to look at the code on GitHub, so before that, let me shut this down. So if you follow the link, you'll see this project. So the producer code is simple. I don't know if you can see anything at all. What I'm doing here is I'm just generating a key value and a message, and I'm creating an object called producer record, and I'm doing a producer.send. So that's all I do in my program. So this program is written in Scala, and this is just a standalone program. Scala. So this has nothing to do. It's not running on a cluster. You can run it anywhere. And this is not using Spark. And the consumer has things like this. So you define what the topic is that you're consuming, and I'm just defining some Postgres variables there, to actually persist the messages to Postgres. And at the beginning of every Spark streaming program, you create what's known as a streaming context. So streaming context is the entry point for your streaming application, and I create a Kafka utils dot create direct stream. Direct stream is that stream that produces all the batch RDDs. So and bulk of the code is here. So stream dot for each RDD. That means for each RDD within that stream, do this processing. So that's all the code is, right? So it's simple code. You can take a look at it, and
so you process the whole messages.
Well, that was just 1,000 messages. So 1,000 messages. It came in, it processed. So it is going in a loop.
Okay.
I think my loop is like 1 second or so. Every second it loops through and grabs all the messages that came in that 1 second. And if you look at it, the producer took just 100 milliseconds or less to produce those messages.
So just you grab in the message and you store them?
Yeah, that's all that's all I'm doing in this application. So once you have that framework, you start building your application from there. Like if you want to do some processing, do it. Yeah. I mean, the point of a demo is not to do any processing. It's just to see how your Kafka streaming works. So with Kafka, you can do producing is very fast. You can do 1 million messages a second on just one node like this. With a consumer, if you have to do some work in terms of processing and persisting, your bottleneck will be your data sync. If Postgres cannot handle that kind of speed, you are limited by that. So you may have to increase the number of nodes and the number of connections to Postgres. That's what you need to do. That's all I have.